Welcome to This Explainer. Today, we're unpacking a massive paradigm shift in how artificial intelligence models actually understand the physical world. For years, we've been pushing the boundaries of what AI can do, right? But honestly, there's been this fundamental flaw in how these systems perceive reality. So today, we're diving into a breakthrough called ODE World. It's a totally new predictive architecture that finally teaches AI to understand time the way the universe actually works. Okay, let's kick things off with a pretty foundational question. In our daily lives, space and time are totally fluid, right? They're continuous, objects move, they interact, they collide, all governed by uninterrupted physical laws. But why do our most advanced AI models still view the physical world like a choppy flipbook? Almost every contemporary AI model relies on what we call discrete time modeling. They literally view reality as a sequence of static, individual frames or steps, completely missing all the space in between. We have a ton of fascinating ground to cover today. We'll start with the discrete time problem, then introduce physical time flow, explore the actual OD world architecture, and finally see how all this unlocks next-level video generation and powers real-world robots. All right, part one, the discrete time problem. Let's look at exactly how standard AI currently struggles to process the reality we inhabit. You can really think of this as the flipbook versus river dilemma. On one side, we have discrete time AI. This approach needs strict data alignment and fixed frame rates. It's incredibly computationally heavy because it literally has to reconstruct reality pixel by pixel at every single step. On the flip side, we have continuous time reality, which is fluid and driven by underlying higher-order physics. Current models are basically just awkwardly mimicking frames instead of actually grasping how one moment smoothly flows right into the next. So the problem really boils down to this. By ignoring the fundamental continuity of physics, standard models are effectively just doing video mimicking. And this leads to massive computational inefficiency. Plus, it means if the data is irregular, or say a frame drops, the AI gets completely lost because it never actually understood the physical laws governing the movement in the first place. Moving on to part two, introducing physical time flow. Let's meet the elegant mathematical hero researchers developed to solve this exact friction. Meet physical time flow, or PT flow for short. Instead of trying to guess the next discrete frame, PT flow conceptualizes the underlying dynamics of data as a continuous latent velocity field. It uses an ordinary differential equation, an ODE, to model how a state smoothly transitions over actual physical time. By completely redefining future prediction as a temporal integration over continuous time, PT flow totally shatters the limitations of that flipbook approach. It's not guessing the next frame anymore, it's calculating the continuous flow of reality. To actually make this framework possible, the architecture relies on two brilliant yet surprisingly digestible mechanisms. First up is dynamical representation decoupling. Imagine you're watching a video of a robot arm moving an apple on a table. Well, the table isn't moving, right? PT flow decouples those time-varying dynamics, the moving arm and apple, from the static background context, the table. The second mechanism is direct first-order supervision. This uses a really elegant mathematical technique to directly supervise the latent velocity field, ensuring the AI is actually learning the correct speed and direction of the movement. Which brings us to part three, the ODE world architecture. Let's see how these concepts build into a tangible, functioning system. Now, it's super interesting to see how the math maps directly into the architecture here. The system uses a pre-trained Dino V2 encoder, which is a vision backbone that projects high-dimensional raw images into a compressed feature space. The data then passes to the dynamics encoder. This is a game changer because it allows OD World to bypass those incredibly heavy pixel-level reconstructions that completely bog down older models. It operates purely in this compact, highly efficient space that's focused entirely on the dynamics of movement. And because of how this architecture is built, it achieves something truly remarkable. In traditional latent models, there's this massive problem known as representation collapse, where the latent space basically degenerates into trivial, useless solutions because the supervision is indirect. But by enforcing ODE properties and using that direct supervision on the velocity field we just talked about, OD World completely solves representation collapse. The model's understanding of the world stays dynamically meaningful. Just look at this visual proof. The data trajectory on the left shows standard discrete prediction models. They are jagged, chaotic, and totally messy, which is exactly what you'd expect from a system just guessing step by step. But on the right, look at the ODE world latent space. It provides these beautifully smooth, continuous trajectories. It has filtered out all that high-frequency jitter. proving the model is genuinely internalizing a smooth, continuous understanding of physical motion. All right, part 4, next-level video generation. This smooth mathematical foundation isn't just theory, it translates directly into some truly mind-bending generative capabilities. Let's look at what OD World can actually do. Because OD World actually understands the continuous flow of time rather than just memorizing frames, it can essentially do the impossible. It can generate video at arbitrary temporal resolutions, meaning it can speed up or slow down motion seamlessly without being constrained by fixed step sizes. If a video is missing frames, no problem. OD World can perform temporal super resolution, flawlessly interpolating the dropped data. And incredibly, almost like sci-fi, because it understands physical laws, it can actually run the math in reverse to generate physically plausible backward predictions. As you can see here, across 4 entirely different robotic tasks from the Libero dataset, like turning on a stove or picking up butter, the generated velocity fields show incredibly consistent, goal-directed convergence. The model maintains its structural fidelity and semantic accuracy across all these diverse actions. This proves it's not just memorizing one specific type of movement, but actually grasping the underlying physics of manipulation itself. And this brilliantly illustrates our payoff. Follow the path of the robot pulling a drawer. The velocity field correctly predicts the instantaneous speed of the robot. It actually knows the robot needs to move quickly toward the drawer, slow down as it carefully grasps the handle, and then accelerate again as it pulls the drawer open. It's predicting highly accurate, physically consistent open-loop plans, meaning it maps out the whole physical motion in advance, and it matches the ground truth reality perfectly. Let's bring it all home with part 5, empowering real-world robots. Because all this smooth math is amazing in software, but how does it translate to a physical robot trying to, say, make you breakfast in the real world? To answer that, researchers tested OD World as a guidance system for policy learning. That's basically the brain that tells a robot how to act. On the rigorous Libero simulation benchmark, the results are pretty clear. Standard baselines achieved around a 76 to 78% success rate, but OD World's sequential subgoals absolutely crushed those established baselines, hitting an 83.6% average success rate. Because its plans are so smooth and temporally consistent, it provides dense, reliable guidance that doesn't drift, which means a lot fewer broken plates in the kitchen. But at the end of the day, simulation is just simulation, right? Well, when researchers applied this OD World guidance to a real-world, physical, bimanual Agile-X robot, it achieved a massive 80% average success rate across highly complex tasks like packing a mouse or multi-object rearrangement. It bumped the success rate of the baseline model from a mere 55% all the way up to 80%. That is a staggering improvement in real-world embodied AI reliability. As we wrap up this explainer, I really want to leave you with a thought to ponder. OD Worlds proves that by abandoning the discrete flipbook and teaching AI the continuous mathematics of physical time, we unlock totally unprecedented efficiency, stability, and real-world capability. Artificial intelligence is finally stepping out of the flipbook and into the fluid river of reality. So, if AI can now simulate the continuous flow of time, what fundamental physical laws will it master next? Thanks so much for exploring this with me today.